Welcome back, everybody. Let's go through one more example of an independent samples t-test. We've already gone through one complete example, and in reality, all of the examples are essentially the same. For example 2, I'm just going to change some of the details, change some of the numbers. We're still going to go through the same 4 steps, and we're still going to make the decisions that we make in exactly the same way. So this is what I want you to do. I want you to work that one out on your own right now. I want you to pause this video and then come back to the video when you have it completed. And then you can check your work against my work. So I'm going to assume that you're pausing the video, and I'm going to keep going, and I'm just going to go through some of the key parts of example number 2. In example 2, we're comparing 2 completely separate groups, so we know we need to do the independent samples t-test. We're comparing 2 different juries, and we're looking at the sentences that they handed down, looking to see if there are differences between those 2 groups. We can see that for the first group, they handed down a 6-year sentence. We can see that there's some variability among the members of the jury. And we can see that for the second group, they handed down a 3-year sentence, and again, there was some variability for the jury. So I gave you the basic descriptive statistics, the means and the sum of squares. Sum of squares, of course, is the basis for computing variability. So we're in a familiar situation. We see a difference between these 2 samples, a difference between 6 and 3. And we're wondering, do those differences represent differences between the 2 populations that those samples represent? It could be that there are differences between the 2 populations. It could be that the differences that we see between these samples just represent sampling error, and there are really no differences between the populations at all. Via these 4 steps, we want to see if we have enough evidence to rule out sampling error as a viable explanation for the differences we see. In step 1, we state our 2 hypotheses. We have 2 competing hypotheses, a null and an alternative. The null hypothesis always states no effect. In this case, no differences between the 2 groups. So we would say the population mean sentence for that first group, when you then subtract the population mean sentence from the second group, would equal 0. In other words, there are no differences. The alternative is that there are some differences. In step 2, we want to figure out how much evidence do we need to reject that null hypothesis. So we create a distribution of differences between sample means. This distribution shows all the differences between sample means that we would expect to find. And keep this in mind too, we create that distribution based on the idea that the null hypothesis is true. And if that null hypothesis is true, we would expect to find lots of differences between those sample means that equal 0. It would be very unlikely to find differences that are this extreme or differences that are this extreme. They do indeed occur by chance, but they do not occur often by chance. Well, where exactly do we list these cutoff points? How exactly do we define those rejection zones? You might recall that we define those rejection zones based on the degrees of freedom, and the degrees of freedom is based on the number of people in each group. According to the information that we have, the sample size is 8 for each group. That means there are 7 degrees of freedom for each group. 7 and 7 equals 14 degrees of freedom overall. In this particular example, we're asked to do a 2-tailed test with an alpha of 0.05. So this is the column that we're interested in. And we're going to look up 14 degrees of freedom. Here's the row for 14 degrees of freedom. If we come across this row, once we reach the 0.05 2-tailed column, we find that we will have critical values at positive and negative 2.145. Positive and negative 2.145. We know we need to do a t-test comparing these 2 means. We know the values for these means. We know that these differences right here are always based on the null hypothesis. And the null hypothesis states that the difference between the 2 population means is 0. So this is always 0. You can essentially cross that out. So we have all the information we need for the numerator, but in the denominator, we need the value for the estimated standard error of the differences between the means. And we don't have that. So I look at the formula for that. According to that formula, I need to know the sample size for each group, and we have that information. But I also need to know the pooled variance, the variance that is combined, that is averaged for those two groups. I don't know that yet. So I need to look at the formula for pooled variance. That's right here. In order to compute pooled variance, I need to know degrees of freedom for each group. I know that because there are 8 people in each group. That means each group has 7 degrees of freedom. And I also need to know sum of squares for each group, and that was already computed for us. So this is where we start. We compute pooled variance, and then we stick it into this formula for standard error. We compute standard error, and then we stick it into this formula for t. And we find a t-value of 3.53. 3.53 is a pretty healthy t-value. Let's see where it is in the distribution of differences between sample means. Remember, right in the middle, we have a t-value of 0. Our critical region is marked off at 2.145. Our t-value of 3.53 exceeds that value. It exceeds that critical value. That means we are inside the critical region. We are inside the rejection zone. So, should we reject the null hypothesis? Yes, we should. Remember, if we determine we are inside the rejection zone, if we say yes, we are inside the rejection zone, then the follow-up questions we ask ourselves should also be answered yes. Should we reject the null hypothesis? Yes. Do we have statistically significant results? Yes. Is it possible that we're making a type 1 error? Yes. And now we move on to step 4 and we formalize all of those conclusions that we just made. So the differences between the means was indeed within that critical region. Remember, it's very unlikely to find that type of difference if the null hypothesis is true. Our data is inconsistent with the null hypothesis. It makes us question the validity of the null hypothesis. And ultimately, we determine we have enough evidence to reject the null hypothesis. In everyday language, what did we find? We found that the jurors who were informed about the withheld evidence gave significantly longer jail sentences. Remember, that value of 3.53, it was located in this little small region, so it should be associated with a small probability. We have to pick between listing a probability p being less than 5% or a probability p being greater than 5%. If we're in this small region, we should pick a small probability, and of the two, which is small, p less than 0.05 is small. And that's what we use right here when we summarize our results for a journal article. The difference that we found is 3 years, and that's pretty easy for all of us to understand. Nonetheless, we're going to compute Cohen's d because it's a standardized measurement of effect size. It allows us to compare the size of an effect across all kinds of studies, so it's really very useful. In this case, we simply look at the differences between the two sample means, that was a difference of 3 years, and then we need to divide by the pooled standard deviation. Remember, we had to compute pooled variance in order to compute standard error. We know that the square root of variance is the standard deviation. So if I know the pooled variance, I can find the pooled standard deviation by simply taking its square root. And that's exactly what we did right here. So Cohen's d in this case was equal to 1.78, which is a very large effect. That's a difference of 1 3/4 standard deviations. Well, recall we used an alpha of 0.05. So if we are going to follow up with a confidence interval, we should do a 95% confidence interval. And that's exactly what we did right here. By flipping around our t equation, we were able to solve for the value that represents the difference between the two population means. And we know we began with the difference between our two sample means, because that's the only information we really have. So we construct an interval of values, a range of values around 3 years. In order to do that, we use the t critical values that we looked up previously, because those t critical values mark off the middle 95% of the distribution. And then to get our answer back into years, not t values, we have to multiply by the standard error. That leaves us with 3 years plus or minus 1.82 years. And that leaves us with an interval of values ranging from about 1 year to nearly 5 years. So the true difference in sentencing between the two types of jurors, some given the withheld information, some not given the withheld information, is a difference between 1.18 years and 4.82 years. And it should make sense to us that we don't see 0 years within that range. Remember, we ruled that out when we rejected the null hypothesis. So one thing we really like about these confidence intervals is by looking at them, we can tell if we have statistically significant results or not. We can tell if we would reject the null hypothesis or not. But then above and beyond that, we also get an estimate of the true value of the population parameter. In this case, we're trying to get an estimate of the true value of the difference between the two population means. 3 years is right in the middle of this range. And as that range becomes tighter, as it becomes more narrow, we have more certainty in that estimate of 3 years. And finally, when it comes to these 95% confidence intervals, they're a good long-term strategy. Because if we were to collect more data and compute more 95% confidence intervals, 95% of the time, those confidence intervals would include the true difference between the population means. But about 5% of the time, the confidence interval that we create would not include that true difference between the population means. And that corresponds with our alpha level of 5%. So I hope you're starting to get the hang of this. All of these examples are essentially the same. Once you completely understand one example, you can do any example. In the next video, we're going to look at the third example. I'll see you then. In the meantime, be safe.